Okay, so last time I was comparing the characteristic polynomial of a hyperplane arrangement to a graphical hyperplane arrangement to the chromatic polynomial of the graph. We have a graph. Then basically you can associate to it this hyperplane arrangement xi minus xj equals 0, I and j an edge. And you can also define the chromatic polynomial of your graph, which is, by definition, chi sub g of t is for t an integer, is the number of proper colorings of g in t colors, which a proper means if you have an edge, then the two colors at the endpoints should be different. And yeah, there is the claim was that the characteristic polynomial of the graphical hyperplane arrangement is exactly equal to the chromatic polynomial of your graph. And let me try an example before I prove this. Well, you already know the proof, but still let me try an example. So let's say I take a graph which looks like this. This is G. So there's two hyperplanes. For every edge, there is a hyperplane. And the hyperplanes look sort of, I mean, if there was a third edge, you would get the Braid arrangement. So you have like 2 out of 3 hyperplanes in the Braid arrangement. And okay, how do I compute the characteristic polynomial of this arrangement? Well, I need to take the intersection poset. What is the intersection poset in this case? Okay, nice. Yeah, so basically looks like this. This is R2. Okay, so what is the Möbius function? And then 1. Okay, thank you. So what is the characteristic polynomial? X minus 1 squared. Yeah, that's the, well, I mean, t a sub g of t squared minus 2t plus 1. And I claim that actually this is not quite correct. I don't know if you can spot there's something wrong with this. This is not the characteristic polynomial of your arrangement. And so let me record the definition again. No, actually, no. It's okay. So here's the definition. What's the definition? Take the sum over all x in your intersection poset of t to the dimension of x times the Möbius function. Okay. Right. Yeah. So the actual dimensions, this is not R2. This is actually R3, because by definition your arrangement lives in R3, and so the dimension is 3, 2, 1, and so we multiply this whole thing by t. That's the correct answer. And similarly, if you look here, right, you try to color, there is sort of t. If you color this in t colors, there is t options for this vertex, and then t minus 1 squared options for the main inverts. The chromatic polynomial of G is t times t minus 1 squared. And these are the same. Okay, now, yeah, and the proof is by deletion, contraction, recurrence. So basically, once you have an edge in your graph, if E is an edge of my graph, then the chromatic polynomial of G is you look at the endpoints of the edge and you either color them in different colors or the same color. And the color is, well, if it's the same color, you're not allowed to do that. So yeah, anyways, the claim is that if you remove an edge, you're allowed to color them in the same color. And then you have to subtract all the colorings where the two colors are the same. So that's precisely you contract the same edge. Does make sense? And that's the same recurrence with signs and everything as for the characteristic polynomial. And you have to check the base cases and stuff like that. And that's basically it. So let me try another example. Let's say I take the Braid arrangement. Say I take Bn, this is the Braid arrangement. How to apply this proposition to the Braid arrangement? Right, what about arbitrary number of vertices? I can barely hear you, but okay, yes. The Braid arrangement is a special case where basically any pair of vertices forms an edge, so that's the complete graph. Take G to be complete graph, and okay, I want to compute the characteristic polynomial of this arrangement. So equivalently, by this proposition, I can compute the chromatic polynomial of the complete graph. What is the chromatic polynomial of the complete graph? N factorial, yeah, that's almost right. So t factorial over t minus n factorial. Okay, yeah, which is just t times t minus 1, t minus n. So that's the characteristic polynomial of the Braid arrangement, which I think we computed previously in a different way. All right, yeah, and let me mention one interesting corollary. So far, everything was pretty sort of trivial, but now, okay, here's the corollary. Let's say I take a graph, I take the chromatic polynomial, and I plug in -1 as the number of colors. What number do I get in terms of your graph G? Okay, so for the arrangement, it's either a number of bounded regions or the number of regions. Which one is it? Regions. Number of regions of the graphical arrangement. What is the number of regions in terms of the graph? No, it's not 2 to the n. Yeah, I mean, it depends on the graph. If it's complete graph, would have been 6. If this graph is 4. It's not twice. Yeah, well, I mean, not, in this case it is, but in general, yeah, we actually had this computation before. I wonder if people can remember. No, not the number of trees. But we did mention number of trees, but that was for the volume of the zonotope. If I can remember it myself. Okay. Any recollection? No? Yeah, okay. The number of regions of the graphical arrangement is the number of, well, I'm so sorry, is the number of acyclic orientations in your graph. Because remember, we discussed that basically every region, if you look at the relative ordering of the coordinates, it gives you some acyclic orientation of the graph. And in particular, so, right? Yeah, now you remember it. Okay. So this is a pretty cool corollary, right? So it's easy to compute the number of regions. It's just acyclic orientations. And then somehow, so if you take the chromatic polynomial and plug in -1, you get an interesting combinatorial number associated to your graph, which you wouldn't, like, if I just started this class by asking, like, what is chi g of -1, or prove that it's the number of acyclic orientations, it's not quite obvious. Anyways, that's the nice corollary. And so, okay, now hopefully I've convinced you that the characteristic polynomial of an arrangement is pretty cool, but still we need some ways to compute it. Next subject is ways to compute the characteristic polynomial of an arrangement. And I already told you 2 ways. One way is by definition. Even though the definition sounds kind of weird, there are, in some examples, especially when things are generic, you can actually compute it, just compute the Möbius function explicitly. The second case, for graphs, let's say you can compute it by deletion contraction. Okay, and I'm going to tell you 2 more ways. So the third one is called Whitney's theorem. (1932). So let's say you have a hyperplane arrangement in RD. Just any not necessarily central or essential hyperplane arrangement, then the characteristic polynomial of t is given by, I'm going to give a formula which looks similar to this, but is different in certain ways. So it's the sum over all subarrangements of A. So just take all subsets of your set of hyperplanes which are central. B subset A such that B is central. And then you take -1 to the size of B times t to the d minus the rank of B. All right. So you have this formula and you have this formula. And first of all, here you have the Möbius function, just hard to compute. Here you have just -1 to the size of your subarrangement. And the coefficient of t here is basically dimension. Here is d minus the rank. If you remember, the rank is the dimension of the span of normal vectors of your central arrangement. So let's try an example. Let's say I have an example where I have a one of our favorite arrangements, which looks like this: A, B, C, and so I want to record all subarrangements B in the sum. Just I want to record all central subarrangements. B, the size of B, and the rank. Yeah, let's do. Okay, so what is the coefficient of t? It's t to the d minus the rank, and d is 2 in this case. T, let's do d minus the rank. All right, so the first element in the sum, which is formally included there, is the empty subarrangement. The empty subarrangement has size 0 and has rank 0. The t squared. Yeah, d is equal to 2. So t. Okay, what are central subarrangements of size 1? Each individual hyperplane. So remember, central means the intersection of all hyperplanes is non-empty. So A, B, and C, these are all of size 1, and they give you a coefficient of t. And then what are the central subarrangements of size 2? A, B, and B, C. 2, and this is going to be, the coefficient is just going to be 1, or t to the 0. So what is the characteristic polynomial? T squared minus 3t plus 2. That's correct. And that's the same we got. Remember, we had this poset like this, and then we computed the Möbius function, and we got the same result. Okay, so if I have an let's try. So if I have an arrangement like this, then if this is A, and let's say B is the same as A, then the rank is going to be 2. Right. Yeah. So it's going to be -1 times t to the 0. Yeah, let's actually, so let's see. There's the empty arrangement here, right, which has size 0 and t squared. And then each individual hyperplane gives you -3t, right? And then if I look at size 2 arrangements, they're going to be, each pair is going to give me a subarrangement of size 2. So there's going to be +3. And then there's going to be one more subarrangement, which is the whole thing. Just all 3 hyperplanes together. It's a central subarrangement, so I get -1. Because the size of B is going to be different. All right, so okay, Whitney's theorem is, I guess, nice. It's non-trivial to prove, but it's, in my experience, it's not as useful as the next thing I'm going to say. So yeah, you should feel free to use that theorem. Sometimes, yeah, in some examples, there's no way around using that theorem, but there is a much more powerful technique, which is, as I promised, a generalization of the chromatic polynomial to hyperplane arrangements called the finite field. Yeah, that's number 4. Field method. Okay, so let me, first of all, it doesn't work for all arrangements. If your arrangement has some irrational coefficients, this is not going to work. So it works only, yes, assume your hyperplane arrangement A in Rd is defined over Z, which means that for each hyperplane, the equation has integer coefficients. Or you may assume rational, yeah, or you may assume that the coefficients are rational, then you can multiply both sides by some integer and get an integer equation. And all examples we had so far satisfy this property. So then you choose a prime. let's say Q is a prime. You can do prime powers. It works for prime powers, but the statements are going to be slightly different. So let's say you choose a prime Q. And then you let FQ be the finite field with Q elements, which we can just take Z, Q, Z. So you can take your hyperplanes and then you can take all coefficients modulo Q. So you get an arrangement of hyperplanes inside FQ to the D. So if R to the, you get an arrangement over a different field. Let A sub Q inside FQ to D be the, so it's obtained by taking all coefficients modulo Q of all equations of the hyperplane. Since they are integers, I can take them modulo Q, and for each Q, I get an arrangement like this. Any questions so far, or so far so good? Any questions? Theorem. For all sufficiently large Q, the characteristic polynomial of your hyperplane arrangement evaluated at Q is given by the, so over FQ, this is a finite set. What you do is you just remove all hyperplanes from this finite set. And you count how much you get, the points you get. Is the size of the complement of your, well, the union of all hyperplanes in your Q arrangement inside of Q. So that is the claim. And when I first learned about this, it was, I mean, to me, it's mind-blowing that there is actually a deep reason from algebraic geometry why this should work, but for us, I guess we can prove it pretty easily. How do we prove this? Well, we can prove this using deletion contractions. So basically, I mean, that may or may not be a rigorous proof, but here's a sketch. We want to show that chi A of Q is equal to chi A minus H0 Q minus chi A contract H0 of Q. So, and you want to show that the same recurrence is satisfied by these numbers of points. Let me try to draw a picture. Let's say I'm going to try to draw a picture. Here's a picture. Here's your hyperplane H0. And inside H0, you have some subarrangement. This is subarrangement inside H0, which is this A contracted H0. Okay, and then you have all these points. If you just restrict to H0, then you have all these blue points in the complement of your arrangement inside H0. So blue is, you take H0, which is over FQ, and then you subtract the union of all H prime in A contract H0 of H. Now there's also outside of H0, there is all these other points, which are, yeah, I guess I'm out of red. Red is you take FQ to the D, and then you subtract all hyperplanes in your arrangement. Okay. Because H0 belongs to your arrangement, so you are not allowed to have any points on H0 on the left-hand side. Does that make sense? So yeah, let me actually finish what I'm trying to say. What I'm trying to say is that if you look at the red point, number of red points is the left-hand side. Because yeah, so just by definition, this is, well, that's what I'm trying to prove. That's the presumably the number of points is on the left side. And here, if you remove H0 from A, that means you're allowed to take points on H0, this complement. So this term here is going to be number of red points plus the number of blue points, right? Because, so if you have a point on one of these restricted hyperplanes, then it belongs to some other hyperplane of A, so it doesn't contribute to this guy. So anyways, the answer here is red plus blue, and then you subtract blue. Yeah. Why don't Q sufficiently large? And yeah, that's a very good question. And the answer is, yeah, so what can happen for small q? Let's say you have a hyperplane of the form xi minus xj equal to 2 or something like this. And then you have another one, xi minus xj equals 0. And these two hyperplanes don't intersect. So if you look at the, let's say, at the intersection poset, these two don't intersect. You can read that off from the poset. Once you take coefficients modulo 2, they become the same hyperplane. Or maybe, or they can start intersecting in weird ways. There is not quite all the coefficients. I think there is an explicit bound, but so yeah, the sufficient condition for Q is that the intersection poset is the same after you reduce modulus. Yeah. Yeah. So the actual applications for us is you treat Q as kind of a variable. Like it's the same as computing colorings of graphs. So you have Q options for this vertex and then Q minus 1 options for that vertex. So you get a polynomial in Q by just some sort of combinatorial reasoning. That works for graphs, but actually for hyperplane arrangements and for the ones I'm going to explain today, I'm going to actually apply this formula to compute things we couldn't compute before. Yeah, that's a good question. So you're asking whether every, let's say I have some irrational coefficients in my hyperplane arrangement, there's a bunch of similar questions. Like let's say you have a combinatorial type of polytope, can you realize it with rational vertex coordinates? And there are some polytopes where you can't, and some polytopes where it's an open question whether you can. I suspect the same is true for hyperplane arrangements. Once the dimension is high enough, you actually get pretty restricted. Yeah, actually, I think. Anyways, yeah, the answer is I think yes. You should get very nasty arrangements. Once you work over different fields, it's not exactly the same. All right. So for the rest of today's lecture, I'm going to try to apply this formula to compute various things. And first of all, let me start with some easy examples. So let's say our most basic example is the Braid arrangement. Then what do? I do fq to the n minus the union of minus my union of hyperplanes is basically, okay, so fq to the n is you just count collections of points, alpha 1, alpha n in fq to the n, and then what are the conditions on these numbers? They should be pairwise distinct. Okay, very nice. Alpha I not equal to alpha j. All right, so how do I count how many there are? Nice, okay. So there's q options for this guy, and then for the next guy there's q minus 1 options because it has to be not equal to the first guy, and etc. So the characteristic polynomial of the n, according to this theorem, q is q times q minus 1, etc. q minus n plus 1, which, so you can notice that you get the same result, but actually the proof is, the reasoning is also the same as for characteristic polynomials as chromatic polynomials of graphs. Just q represents the number of colors in this case. And yeah, similarly for arbitrary graphs, if you have a graphical arrangement, then you're looking at the set of points alpha 1, alpha n, such that alpha I is not equal to alpha j if I and j form an edge. So just you get literally the chromatic polynomial. Again, q represents the number of colors. Let me actually mention some other pretty cool application from a while ago. So let's say you have a root system. Let's say you have a root system, and then you take the orthogonal complement to every root. So by definition, alpha perp, where alpha is a root. Yeah, then for type A, you would get the Braid arrangement, but for other types, you would get other interesting arrangements. And if you try, yeah, that's probably going to be in the homework. So there's going to be homework pretty soon, hopefully tomorrow or something like this. I don't know. And yeah, so maybe I'll include this into the exercise. Compute the characteristic polynomial for, let's say, for classical types, for types A, AN, BN, CN, and ZN. There are nice answers for each of them. And if you, yeah, the key here is to go to Wikipedia and look up the explicit coordinates of roots, and then they're defined over the integers, and so you take the modulo q, and you can actually pretty easily find out the characteristic polynomial. So that's already, I don't know any other way to compute this example without the finite fields. Okay, and finally, let me now try another example that we had before. It's called the Xi arrangement. So at the beginning, I announced all these different arrangements that we're supposed to be able to tackle. So the Xi arrangement, if you remember, is xi minus xj is equal to either 0 or 1. I is less than j. And the picture we had, so you take the Braid arrangement, and then you shift every hyperplane one step up. This is 3. Okay. So what's the number of regions of this arrangement? Okay, here the number of regions is 16. Number of bounded regions, 4. Okay, and I promised that this would be n plus 1 to the n minus 1. This would be n minus 1 to the n minus 1. So now, finally, I should be able to explain this, why this is true. So theorem, the characteristic polynomial of the arrangement is t times t minus n to the n minus 1. In particular, so if you plug in -1, you get -1 minus n. Basically, after the sign, you get n plus 1 to the n minus 1. And if you plug in 1, this becomes t, well, this becomes 1 minus n. You get n minus 1 to the n minus 1. Okay, so that's the, again, you see that this factors very nicely. And how do I prove this? I'm going to prove it using the finite field method. Is the number of alpha 1 to alpha n in fq to the d such that alpha I is not equal to alpha j or alpha j plus 1. Okay, that's the, I'm trying to count the number of colorings, let's say, right? I have q colors, but my conditions on colors are sometimes that if I, so this is for I less than j. Right, so if vertex I is less than vertex j, then the colors have to satisfy a more general condition here. And yeah, let me try to, I'm going to have a random example. So I'm going to give you a proof. Proof is sort of tricky, so let me start doing an example right away. So let's say I have an example where p is 11 and n equals to 6. What I'm going to do, I'm going to draw the whole f. Yeah, oh yeah, let's do, instead of q, let me switch to p. P. Otherwise, I'm going to get confused. So let's say I draw 11 numbers. 0, 1, 2, 3, 5, 6, 7, 8, 9, 10. Here is 11 numbers. These are elements of FP. And then I'm going to try to choose alpha 1. Let's say I choose, yeah, I would ask you to choose an alpha 1 for me, but let me actually choose an alpha 1 myself. Let's say alpha 1 is equal to 6. So I'm going to place 1 at position 6. Then if I look at alpha j, for j not equal to 1, what are the restrictions? J bigger than 1, alpha j should not be equal to what? 6 or 7? Actually, 5 or 6. So I'm not allowed to use the same number twice, and I'm also not allowed to use 5 anymore. So whenever you place a number, all the next numbers cannot go either here or here. So I can, and now I can keep going. Maybe I should choose, maybe my alpha tuple is 6, and then 2. Oh, sorry, 6 and then 1. I get confused between these numbers and numbers, but yeah, alpha 2 is equal to 1. And therefore, I'm not allowed to use 0 anymore. And then let's say alpha 3 is equal to 2. 6, 1, 2. Yeah, let's do 7, 9, and 3. So alpha 3 is equal to 2. And that I'm allowed to do. I'm not allowed to go here, but I am allowed to go right next to the 2 in the other direction. 1, 2, 3, 4 here. 5 is here. And then finally 6. Okay. So I'm trying to arrange these numbers on the circle, placing them on all different positions, and I'm trying to count in how many ways, how many combinatorial pictures like this do I get. That's the goal. Any questions so far? Okay, so, and then I'm going to do this in a kind of roundabout way, but the idea is basically I'm going to, okay, so let me actually write down what I'm going to do. I'm going to choose a partition. Choose a partition pi of b1, b2, etc., b p minus n. This is called a weak partition of bracket n. So what this means is that the disjoint union of all these p's is equal to bracket n, and any two different parts are disjoint. So for the example on the right-hand side, the partition I'm going to get is 5 equal to 1, 4, comma 5, empty set, 2, 3, 6, empty set. And the way this works is that 1, 4 is here, and then you skip one element. And then 5 is here, and then you skip one element. And then the empty set, and you skip one element. And then 2, 3, 6, you skip one element. And then the empty set means you skip another element, and then you get back to your original picture. So usually for partitions, you're not allowing empty sets as a part. So it's a weak ordered partition. Of bracket n into p minus n parts. Yeah, and then let me now explain properly what I just hand-waved when I said. I'm trying to, so I have chosen my partition, which, by the way, in how many ways can I choose such a partition? Yeah. Okay, so hold on. No, it's 1, 2, 3, 4, 5. 5 is p minus n. Oh, sorry. Yes, okay, you're right. P minus n. Yeah, okay. So in how many ways? Number of ways to choose pi. Oh, there should be another condition. I want and I want 1 to belong to B1. Minus n to the n minus 1. Right, so I can place 2 into any of these parts and 3 into any of these parts, etc. So it's very easy to compute the number of options for pi. And it looks related to that number over there. Okay, so now I need to go from pi to an arrangement like this, which is an alpha tuple, alpha 1, alpha n. What I do is, so I need to, as you see, the two numbers are not exactly the same. So I need an extra choice. Choose where one goes. Okay, so indeed, the first step is choose alpha 1, just an arbitrary point on the circle, and place 1 over there. And then after that, you basically place 1, 2, all the way. Yeah, you place elements of B1 in places alpha 1 plus 1, etc. Alpha 1 plus the size of B1 minus 1. So here B1 is 1, 4, so I place them in increasing order. Place elements in increasing order. And then I skip one spot, and then I place elements of B2 in places. So I skip one spot and I get alpha 1, size of B1 plus 1, I guess. And then you skip one more spot, and etc. So because there is exactly p minus n parts, that means I'm going to skip exactly p minus n spots. And then and because the union is bracket n, I'm going to place exactly n elements on the circle. So let's see. The first part is 1, 4. So I put 1, 4, and then I skip one spot. And then I have 5, and I skip one spot. The empty set, yeah, it's all. So the empty set means I skip this spot, and then 2, 3, 6, skip here, the empty set, skip here, and I get back to exactly where I started. So everything works out very nicely. And I guess an exercise is that, so claim is that in the resultant tuple, so I converted alpha 1 and p into this tuple, and I claim that it satisfies these conditions that define the shoe arrangement. Alpha I is not equal to alpha j plus 1 if I is less than j, and this is a bijection. So bijection, if you have an alpha tuple, I claim that you can reconstruct alpha 1 and pi from that tuple by just looking at the circle and the partition of these blocks on the circle. So that's it. That's basically the whole proof. Any questions on the proof? All right. Yeah, and I think this is a sort of important transition for us because, well, this number n plus 1 to the n minus 1, it shows up in combinatorics. Yeah, number of trees and number of parking functions and all these other things. So what we see here is that you start with a cool arrangement, like some sort of natural arrangement, and then it reduces to counting some combinatorial objects. That's the interplay between geometry and combinatorics, and you have finite fields somehow show up in here. Yeah, so next time I'm going to briefly mention the Catalan arrangement, as I promised, and then I'm going to switch to matroids. So thanks, and see you all on Wednesday.